Assalamu alaikum warahmatullah. Now we move on to discussing unconstrained optimization, meaning what? That the independent variable, in our case it's the x here, our example, is not constrained, so it lives in the whole space, right? So let's say something like this. Okay, let's say that we have a function f of x, and we want to find its minimum value, so we write minimize f of x. This is a simple minimization problem or an optimization problem. Now here, of course, x, you can write here x lives in the real line, so this is an unconstrained problem. Why? Because the independent variable here, x, is not constrained. It lives in the, it can take values, any value, from the real line. Okay? So this is an unconstrained optimization problem or a minimization problem. So how do we solve this problem? It is simple actually. We just take the derivative of this function and we equate it to 0 as we said earlier. So let's take an example, right? Let's say that we have a loss function, this loss function, right? Which is a fourth order polynomial, right? If you plot it as we did in figure 5.1, you can see that it has a global minima. So this is global minima. Here you have a local minima. So let's write it correctly. Okay, it's not working. Anyways, so it is a local minima, and you can notice here that we have a local, in a sense, maxima. So you have two minimal values and maximum and one single maximum value. You can, if x is unconstrained, so this function goes to infinity in this way, goes to infinity in this way, maybe it wiggles a little bit, but in the end it goes to infinity, right? So because if you take the limit of the x goes to infinity, this will go to infinity as well, right? Okay, so how do we find this global minima? As we said, we take the derivative, right? We equate it to 0, then we find the solutions. So the derivative gives us a third order polynomial, so it has 3 solutions. Those 3 solutions correspond to those 3 values, this one, this one, and this one, right? So which one is the minima? To find out which one is the minima, we take the second derivative, okay, and see and which one of the stationary points. The stationary points are the points that give us 0 first derivative, right? So we see which one of the stationary points gives a positive second derivative. If it's a negative derivative, a second derivative, this means that this is a maximum value. Now, is it a local minimum or a local maximum, actually we cannot know. We have to compare the two of them, right? So this is one drawback of using this conventional method. We cannot know if the stationary point is at the local minimum value. Okay, now we've been talking about a scalar function. How about a multi-valued function? So we have x takes a vector from Rd to a scalar value, right? We're still talking about unconstrained optimization now. So the form of the minimization problem is given in 5.4, right? The solution is denoted by x star, so this is the optimal value. This is called argument. So this means that give me the argument of the minimizer of f of x, right? So in this case, when x is a vector, being x lives in a higher dimensional space, it's difficult to use the conventional way, right? So one way to do it is to search all the space, but this is very expensive. So what we do is that we, as we did before, we take the gradient. So how to solve it? Say okay, we get the gradient with respect to x of this f of x and we equate it to 0, right? Now this equation might not have a closed form solution. So what we do in this case, we have to search the space, but we do it in an intelligent way. We use what is known as the gradient descent algorithm, which is a very popular and widely used algorithm, especially in machine learning applications, right? So in a nutshell, let's take let's write a simple example like this. So let's say that, okay, let's say that x belongs to r squared, right? So we have now, we want to find the minimum of f of x, right? Sometimes they write here underneath the minimum the domain that you want to search. X lives in or belongs to r squared, right? So let's say that we'd like to draw this function. So here's R2 space. So let's say that this is x1, this is x2, right? And this is the f of x, right? So this is f of x value. So let's say that, okay, we have a nice convex function. So we have something like this, right? So let's erase this, right? And just sorry, to simplify matters, let's do it like this. Okay. So and this is our quadrant, let's say, and we have the minimum value. Let's put it in a different color, green, right? Okay, this is our x star, the solution, right? Okay, how to find this? Now, technically speaking, if this is a hyperbolic function, you can find the solution easily. But let's pretend that we don't know that the function is a hyperbolic function. What we do is that we start with a guess, initial guess, x node. Let's say that x node is here, let's put a different color now, orange, right here. So this is x node, right? And okay, we want to search for the minimum value of the function f of x. So what to do? First, we need to find the direction of the minimum value. How to find the direction of the minimum value? We recall that the derivative gives us the direction of increase of the function, right? So if we take the gradient of f of x, this actually is increasing direction. But we are not looking for the maximum value, we're looking for the minimum value. So we need to look at the negative of the gradient or the Jacobian, which is this is a vector. Recall this is a vector. A vector meaning a direction. Okay, so now we want to move from x node in the direction of the negative gradient. Okay, so how many steps, how many units? Actually we don't know, so let's call it, what did we call it above here? We called it gamma, right? So let's be consistent and we say okay, let's move gamma units in the direction of the steepest descent, and this will give us our new guess, x1. And we keep iterating, we find x2 in the same way, x in the same way, until we get a small value. Okay, how do we stop? Say okay, when we reach the minimum value, the gradient ideally should be 0, but since we are not in an ideal world, maybe we have some kind of round of error or something like that, we would like to stop if the norm, say the magnitude or the norm of the gradient, is less than some small value epsilon, right? So this is the way that we implement the gradient descent algorithm, which is an algorithm, an easy algorithm, effective algorithm, but not very fast algorithm to find the minimum value of any function. Now we need to note that it will find the minimum value but not the global minimum value. It will find the minimum value. Is it a local or global one? We don't know, and we hope that it is a global one. Okay, so this is the algorithm written in a formal way, right? So we give it an initial value, the stopping tolerance, number of iterations, so we don't end up in an infinite loop, the learning rate, or this is the step size. Some books or literature papers call it step size, right? And we start with this initial guess and we iterate until n values or n times. We compute the gradient, we check if the gradient is so small, we stop, otherwise we update our guess with the new value, right? Okay, now how to find gamma? Gamma, we can find it using a different algorithm called the backtracking line search. Why I call it line search? Because gamma is a scalar, so gamma in a sense lives on the real line, so we need to search the real line for the best value of gamma. So this is a new optimization problem, but one regarding finding gamma, right? So there's different algorithms, but the best one, or the one of the most popular ones, is the backtracking algorithm. So here we start with gamma equals 1, right? And then we compare the value of our guess. Remember, this is our guess, new guess, with the, let's say this is the the secant of the function, right? If the value of our guess is greater than the secant, then we update the gamma by multiplying the old gamma with some beta. Beta is a value between 0 and 1. Okay,